Okay, so next up, we'll be doing some thermal and throw in what happens with Poisson when we get some Poisson's ratio effects in there as well. So we'll get this steel block. I'll go with some A37 structural steel because, again, it's in the back of the book. The block starts off measuring 39.9 millimeters in the X direction, 30 millimeters in the Y direction, and 40 millimeters in the Z direction. And it is thrown into a rigid container that is carved out with a carved out section that's 50 millimeters in X and 40 millimeters in Z, and then the top's just left open. So we insert that block into that container, and it starts off quite snug in the Z direction, but it's got a 0.1 millimeter gap in the X direction left. So the block is heated up. When that occurs, I'm asking at what temperature does the block close that 0.1 millimeter gap, and what are the stress and strain states at that time? And then, additionally, what if the block is heated an additional 20 degrees Celsius, and then what's the size of the block at that point? So, someone who doesn't know what they're talking about might just be like, oh, well, this is easy to solve. I know that the thermal strain needs to be enough to close that gap. I could calculate that by just looking at this 0.1 divided by 49.9 millimeters. It'll give me a strain of 0.002004, blah, blah, blah. And just take that, divide by our thermal expansion coefficient, and that gives us our delta T. No, that is not the case, and that is due to the fact that essentially when you start heating the block, it's not free to expand in all directions. It is constrained by the fact that it is quite snug across this dimension here. The 40 millimeters there, it is not free to expand at all in that direction. So as a result, when it tries to expand in that direction, instead of expanding, it gets squeezed. It would expand, but instead it tries to push against the walls. And since the container is completely rigid, the walls push back enough that it doesn't expand. So its total strain in the Z direction needs to be 0. So we need to basically figure out what sort of stress would be causing, what sort of stress would need to be applied to the block in order to counteract that expansion effect. And then once we do that, we can figure out what effect that will have on the expansion in the other directions. So so our known conditions are we know how much the final strain is. That much is true. We calculated the final strain enough. It's just not all due to this. We calculated the final strain, and we know that the stresses in the X and Y direction are all going to be 0 because at that point the block is still completely free to expand in those directions. It's only constrained in the Z direction, so there's only going to be stresses that are building up in that direction. So just to take this, so we got a nice little matrix form of the generalized Hooke's law. I didn't include the shear strain portion of it because it's all just ones and zeros. It's all going to be zeros for the stresses, so it's all going to be zeros for the strain. So don't worry about it. But anyway, so we got our nice matrix form of the generalized Hooke's law, and then we're adding this term here for the strain caused by the thermal expansion. So we can just plug stuff in there. We know our known values are, we know what this is, we know that this is 0. So the first kind of known that I'm going to plug into our equation here is the x strain line here. So we know that the stress in the x and the stress in the y are all 0, so cancels out that term, cancels out that term. So we're left here with the strain in the x is equal to 1 over Young's modulus times negative Poisson's ratio times the stress in the z direction plus this thermal term here. So that's we got one equation there and we have two unknowns there. So let's move on a bit and try to find something that we can solve for a bit more directly. So how about we look at this equation here? So that one's fairly simple because we have we're basically able to we know that these two terms here with the Poisson's ratio, those are 0 because the stresses in x and y are 0. So we end up with just the strain, which is 0 total, is equal to the stress in the z direction divided by E plus the thermal expansion times the coefficient of thermal expansion times the delta T. So we're able to solve for our z direction stress in terms of the delta T. And then we can take that and we can plug it into here, and then we can basically help. Then we're down to just the single unknown, so we can solve for that. So the e's cancel out when we do this. So we are actually left with 0.002004 is equal to 1 plus Poisson's ratio times our thermal expansion term. So based upon that, we can solve for delta T just by dividing by these, and that gives us a once we plug the numbers in, it gives us a delta T of 126.5 degrees Celsius. Then once we got that, well, we can go back to this equation here, and we can plug in our numbers and then solve for what our stress state is at that point in the z direction. So that ends up being negative 303.6 degrees, sorry, 0.6 MPa. And again, at that point, the X1 just started touching, so it hasn't grown enough to, it hasn't tried to start pushing against that ball. It's just kind of at the point. This is where it starts touching, so its stress is still 0 at that point. Any additional temperature change will cause that to increase, and our y is also 0, and then all the shear stresses are 0. So here is our stress state tensor, and then we were asked for the strain as well. So EY is going to be equal to this equation here. We'll notice, that's just going off this and tossing out any terms that are 0, but you'll notice that that is actually equal to the same equation that was used here to calculate the strain in the x direction, or sorry, that was used to calculate the delta T from the delta T and the z direction stress. So if it's the same formula, that needs to be the same amount. So that ends up being equal as well. So which isn't surprising because otherwise there's there's no differences between the between kind of the strain or stress state that would be induced. The only stresses that are if the only stresses that are arising are in the z direction, then the strain in the strain in the x and y should be identical. So we end up with a strain state of this. So part B though, what happens if we instead decide to ramp up the temperature a little bit more? So we're increasing it to 146.5 degrees Celsius. Delta T, again, from whatever the baseline was. I didn't specify an initial temperature condition, but to a large degree it doesn't matter too much as long as you don't start getting to the point where it's so hot that you're changing the Young's modulus. That could be a thing. But we'll assume for the time being that the temperature, if we're starting off around room temperature and we're talking steel, that's not really going to be a big deal. So again, we're just working from our nice little generalized Young's modulus formula here. I went ahead and plugged in our delta T here, our other knowns. So the y direction stress is still going to be 0. It's still completely free to expand in the it's the top's still open. It's still free to expand vertically. There's nothing stopping it from doing that. The strain in the x is going to be the amount we calculated previously, because that's the point where it hit the wall, and then any additional heating is going to be stopped by the wall. Our strain in z is still 0, and our delta T, again, I already plugged that in. So looking at this, I'm going to start with the EZ term again. So I'm going to just plug that into here. So we got right now we got two unknowns in this equation. We know what the delta T is, so we know what the strain caused by that is. So our unknowns are just our x and z stresses. So I went ahead and solved for this in terms of the z stress. So added everything else to the other side. So first off, multiplied by e. To get rid of that, so that times e gives us that, and then just subtracted the terms from either from this side to get to the other side. So the subtracting the negative Poisson's ratio x stress turned that positive, and this turned negative, and then we're just able to solve for the stress in the z direction easily in terms of this constant and this other constant times the x direction stress. And I could have easily plugged that in there too, but I didn't bother yet. Next up, well, we know what the result in here is, so we're going to plug that in. So we've got our known strain, and then again just our x stress divided by Young's modulus minus our Poisson's ratio times the z stress divided by Young's modulus, and then again our expected thermal expansion at this temperature. That's the thermal expansion we would see if the thing was completely unconstrained. So this here minus this here gives us this here, and then just plugging in our few of our numbers. So we got divided by E got the Young's modulus, sorry, the Poisson's ratio divided by the Young's modulus, and then of course I just took the sigma ZZ and plugged in the equation that we had previously solved for it as into here. So that ends up being and then for the next step I just went and multiplied by Young's modulus to kind of get rid of these terms and turn this strain into a stress. So it turned into a 49.2 MPa, and that gives us, we're left with just our stress in the x direction minus the Poisson's ratio squared times our stress in the x direction, and then plus Poisson's ratio times that 351.6 MPa. So basically the two negative signs that we have here cancel out. That turns into a plus. So we're able to take that, figure out what that is, and then I think it ends up being like 90 something. Subtract the 49.2, subtract that from the 49.2, which gives us a negative 63.3 MPa, and all that's equal to 1 minus the Poisson's ratio squared times sigma xx, solving for sigma xx by dividing by this term, which I think ends up being like 0.89 something, gives us our sigma xx, which is negative 70.5 MPa. So again, compression, not surprising. Any of the stresses we see here should be compression. You're never gonna. You're never, if something tries to squeeze into a wall and the wall pushes back, it's never going to push, it's never going to pull back. Walls don't pull at you. Walls push at you. So anyways, the Z direction. We already had this nice formula here for the Z direction, so negative 70.5 times Poisson's ratio minus another 351.6 gives us this negative 374 MPa. So again, it shouldn't be surprising that the compressive stress in the Z direction is a lot more than the compressive stress that's going to arise in the X direction, because it started getting squeezed from the very beginning, as opposed to the X direction one, which only started getting squeezed for the last little bit. So we got that. Now we can solve for the strain in the Y direction, and that's just, that's just taking this formula here. So negative Poisson's ratio times the stress in the X minus the negative Poisson's ratio times the stress in the Z. Well, also plus the stress in the Y direction, but it's 0. All that divided by our Young's modulus plus our thermal expansion term gives us the strain in the Y direction. So it's squeezing out. It continues to squeeze, so it gets squeezed it expands just due to its thermal expansion, and also kind of the other dimensions get squeezed enough to push it out even further. So its strain is going to be that. The strain in the Y direction, in the X direction is the same. Strain in the Z direction is still the same, because again, the walls that are pushing back. So this is our strain state, and here is our stress state. So finally, we're asked to figure out what the dimensions of the block are at the end. Looking at this, so we know what the dimensions are of the block and the X and the Z. The Z didn't change at all. The X expanded until it hit the wall, so it's at 50 millimeters now. The Y, well, okay, we don't know that yet. We know what the strain is, so we know that the strain is that, which we can use to calculate our delta L. So the delta L is just going to be our strain times the original length, which gives us 0.0741 millimeters, which means that our ultimate size of the block is going to be 30.074 millimeters. So again, this is not a large change in shape. This is something that, if you were just observing it, you would be hard pressed to see it. I mean, you might be able to see, the little gap here closing, this little gap here closing. But again, I exaggerated this on the diagram. The gap is 0.1 millimeters in a 4 millimeter, in a 50 millimeter space. So it's really small and it closes up. Okay, so it'd be hard to see that. So we're not talking large changes in size. I would like to point out we are talking fairly large stresses being induced here. The Z stress there, that's 374 megapascals. So if we just go to our chart here, we're looking here at the A36. We're looking here at the A36. So its yield strength, hey, guess what? We've exceeded that already. We exceeded it before we even closed that gap. So this thing, once it shrinks back down, it is going to be changed permanently as a result of that. So you don't need large deformations to start causing damage. You don't need large temperature changes to be causing a lot of stress. And especially if the material in question is constrained against some, if the material in question is really stiff, like steel is, if it has a high modulus of elasticity and it's constrained, its ability to withstand temperature changes without causing a lot of forces that could damage it, it's rather limited. So large temperature changes, they can cause havoc. So they need to be taken into account. Your thermal expansion needs to be taken into account when you're designing components.